Hello, students everywhere. Today I'm going to talk a little bit about Newton's three laws of motion, one of the greatest discoveries ever in the history of the human race. Newton's three laws of motion. They've allowed us to go to space, they've allowed us to send rockets to the moon, they've allowed us to send people to the moon, and they also work for your bicycle or motor car going along the road. Newton's three laws of motion, one of the greatest discoveries ever in the history of the world. Now, let's try and put it in a bit of historical context, because to understand physics and to appreciate how important things are, you've got to look at the background a little bit. No point just learning Newton's three laws of motion. You need to know about what came before that. And it started, of course, with Isaac Newton here. And Isaac Newton, a remarkable man. And you know, Isaac Newton was studying at Cambridge University. And then a terrible illness struck the whole of Europe. It killed millions of people. And because this illness was going on, all the universities and schools in England closed down. So Isaac Newton had to leave Cambridge University because it had closed down because of the illness. And he went to stay in a small house just outside Cambridge in the countryside. And that's where he made all his great discoveries. That's where the apple is supposed to have fallen on his head in the kitchen garden. And the tree, the apple tree, is still there. You can go and visit it if ever you visit England. So Isaac Newton, a remarkable man. Now, Isaac Newton not only discovered his laws of motion, he also discovered the telescope. He also discovered the fact that light, white light, is made up of a whole lot of different colours. I'm going to tear Isaac Newton off there now. And he also discovered the calculus, differentiation and integration, all thanks to Isaac Newton. But something Isaac Newton did was a bit weird, a bit odd. He spent a lot of time doing experiments to try to turn lead into gold. And people who did that were called alchemists. And they were really a bit weird. It was all a bit rather like magic. And some people thought it was involved devil worship. And here is a painting of what people thought an alchemist was like in the 1500s, working away in his funny laboratory. And nowadays, you even have films called The Alchemist. And the idea of an alchemist today is somebody very odd, very weird. Here is a typical picture of what we think of as an alchemist today. But you know, alchemists were not all stupid. They did some very good scientific work, and in particular, they introduced the idea of carrying out experiments. And so the alchemist in our mind here, of which Isaac Newton was one, they are the forerunners of what we have today, the modern laboratory. And here is a modern biological laboratory with a young lady working out or trying to find out a vaccine for the coronavirus. So Isaac Newton's life was at a time when this great illness was going around and things were in great turmoil. But he stayed in his little house. He was, if you like, he was in quarantine. And he stayed in his little house and he thought, and he thought, and he thought. He didn't just go to sleep or play on his mobile phone. There were no mobile phones in the days of Isaac Newton. I hope you know that. He didn't just laze around, he actually thought a great deal, and he wrote books. And he wrote his great Principia Mathematica, in which he wrote down his three laws of motion. But you know, people thousands of years ago were thinking about movement. Aristotle was a Greek philosopher. He lived 2,300 years ago in ancient Greece, and he thought about movement, and he came to two ideas. First, he said, to keep moving, you have to have a force. It sounds sensible, doesn't it? Secondly, he said that heavy objects fall faster than light objects. That sounds quite sensible too. But he was wrong. He got it completely wrong. But for 1,800 years, everybody believed that Aristotle was right. But he wasn't. He was wrong. And it needed Galileo 1,800 years later to actually show that poor old Aristotle, the Greek philosopher, got it completely wrong. And Galileo showed, incidentally, if we think of history again, Galileo lived from 1564 to 1642. And when you think about it, 1642, that was the days of the Shabdrung. So Galileo was arrived when the Shabdrung was building the Dzongs. So Galileo, he carried out 2 experiments. He dropped a big cannonball and a little cannonball from the Leaning Tower of Pisa, which is a tower in Italy which is leant over like that. And he dropped the cannonballs down. They hit the ground at the same time. Aristotle was wrong. The heavier one didn't travel faster than the lighter one. And he then rolled a ball down a simple wooden slope. And then he made the slope go like that, and he rolled the ball, and he saw the ball went down and then up, down and then up. And then he made the slope a bit more shallow. The ball went down and up, down and up. And then he got the idea, if he made the slope level, the ball would keep on going. Newton's first law. The ball would keep on moving forever and ever. And then that was the beginnings of the idea of Newton's first law. And then a French scientist called Descartes, he actually wrote a book in 1644 in which he wrote down what in effect is Newton's first law. Now, Descartes wrote that book when Newton was still wearing nappies. When Descartes wrote that book, Newton had only just been born, so Newton's first law should really be Descartes' first law. So Newton's 3 laws of motion ought to be 2 laws of motion. Newton's first law was first written down by Descartes, but fortunately Newton's second and third laws, they actually do belong to Newton. And as I said, Newton's laws of motion are one of the greatest discoveries ever in the history of human beings. And they completely revolutionized our lives. And we have Newton's third laws to thank for everything mechanical, from planes, rockets, boats, cars, bicycles, scooters, everything mechanical, everything that moves on the earth, we have Newton to thank. Well, now, I'm going to now talk about Newton's first law. And before we talk about Newton's first law, let's just think about what it says. Now, Newton's first law is written down in your textbook, and I'm going to show you the textbook that I'm referring to, just so that you can check whether it's the one you have at school. Well, now, the textbook that I think you have at school for class 11, where all Newton's laws of motion in, is this Fundamentals of Physics, class 11, by Halliday, Rennick and Walker. And here are the pages all about Newton's laws of motion, first law of motion, and I'll be referring to it a bit later. So if you have this book at home, Fundamentals of Physics, get it out and have a look, and you'll find on page 142 things about Newton's first law. Well, now, what the book says about Newton's first law, the book says, a body continues in a state of rest at a constant speed along a straight line unless compelled to change that state by a net force. Now, that's quite a lot of words, and I expect you're going to learn that off by heart. But there's no point of learning it off by heart unless you know what the words mean. And we've got some funny words in there. A body. Do we mean a dead body or a body lying on the ground? No, it means something, an object. It might be a car, it might be a space rocket, it might be a ball in a game of football. A body means an object. A state of rest. Well, we talk about the state of the Union of India. We talk about the United States. State simply means what it's doing at the time. So a state of rest means it's not moving, it's stationary. At a constant speed. Constant means not changing. There's a lovely line in Shakespeare, I am as constant as the northern star, because the North Star in the sky stays in the same position. Constant means not changing. Along a straight line, well, that's easy, unless compelled. In other words, made. If I compel you to do something, I make you do something. Unless compelled to change that state by a net force. So in physics, a net isn't the same thing as a basketball net or a volleyball net or a fishing net. Net in physics means the total result after you've taken everything into account. After you've thought, for example, a net force, after you've looked at all the different forces acting, what's left when you add and subtract. So Newton's first law, a body continues in a state of rest at a constant speed along a straight line unless compelled to change that state by a net force. Now, one of the problems about physics, especially in a textbook, is you can often have too many words. Too many words makes it complicated. So my version of Newton's first law is this. If you want to speed up or slow down or change direction, you need a force. That is Newton's first law in simple words. If you want to speed up or slow down or change direction, you need a force. Pretty obvious, isn't it? You know you need to push something to make it start moving. You know you need to push something to make it stop moving. You know that if you want to go round in a circle, you need to push on the side in order to go round the circle. So, I repeat, if you want to speed up or slow down or change direction, you need a force. Now, I'm afraid for the exam, you probably need to know the longer version. So do remember it off by heart if you like, but remember all it's saying is that. And this is one thing always, when you're reading your physics in your textbook, there are many, many, many words, lots of words. What you should do is try to say the same thing in simple words, using short sentences. And this is where your teacher can help you, by turning all the words into the textbook into short, simple sentences and short, simple ideas. Don't get lost in all the words in the textbook. But if we go back to the long version, a body continues in a state of rest at a constant speed along a straight line unless compelled to change that state by. Now, the textbook says a net force. I've added in red here the word external force, because the force has to come from outside the object you're looking at. And in a minute, we're going to go down and look at my Hilux, and I can illustrate to you what I mean by a net external force. So, this is what you should remember off by heart. It's the statement in the textbook, but I've just added the word external force there. And if you want to know what it means, then remember the short version. Right, so now we've come down to have a little look about what I mean by net external force. 2 words, net external. Now, let's look at my Hilux here. And it's on more or less level ground at the moment. Let's think about the forces on it. First of all, we've got the weight of the car, the force of gravity pulling the car down. Why doesn't it disappear into the earth? It doesn't disappear into the earth because here and here we've got the force of the earth pushing up on the car. And this brings us to what we'll cover later, which is Newton's 3rd law of motion about action and reaction. So we've got the weight pulling down and we've got the reaction of the ground pushing up. The 2 of them are equal and opposite, so they cancel out. So the net force is 0. So the car doesn't fly up in the air, nor does it sink into the ground. And it's on level ground here, more or less level ground, and so there are no forces forwards and there are no forces backwards. So the car remains stationary. However, if I get my granddaughter here to exert a force on the back of the car, she's a very, very strong girl, and if you come round here and push the back of the car, now, don't push yet, otherwise it's going to roll down the hill. Now we have got the downward force, the weight of the car, the upward force of the ground pushing the car up, balancing out so it neither goes up or down. But when my granddaughter pushes the car, I've got a forwards force and there's no opposing force. So the net force is a forwards force from the strength of my granddaughter here. Now, let's see what happens when she really pushes. Are you ready?
Yes.
Sonam? Push! Wow! And there you see the result of there being a net force. So, if we were to draw a picture of this car and draw arrows to show the forces, we would have an arrow down, which is the weight of the car. We'd have an arrow up, which is the reaction of the earth on the tyres. We would have an arrow forwards, which was the force of Sonam pushing, but there's no arrow backwards. So therefore the car starts to go faster and faster forwards. But once the car is moving, what do we get? You stick your head out of the window, but be very careful, don't do it on the road, and you'll feel a wind blowing. Because once the car starts moving that way, we get wind resistance, air resistance. So now, Sonam, if you start pushing the car again and make it go faster and faster. Ready?
Yes.
Push! Well done. And now air resistance is coming in, and the air resistance acts backwards. So we're going to go back to draw a picture of the forces acting on the Hilux. So a net force means that when you look at all the forces in different directions, they all balance out to 0. They all cancel each other out. But what does an external force mean? Well, now, I've got 3 kids in there, and they're going to push forwards really hard. Okay, kids, push, push, harder, push, push. The Hilux isn't moving. Why not? Because that isn't an external force, it's an internal force. If I think about the Hilux and the children in it, There is no outside force pushing. They are pushing, but they're part of the hilux. So therefore, the hilux doesn't move. So when we say an external force, we mean there has to be a force outside the object that we're looking at. If you take a ball that you're going to throw, inside the ball there are billions of little molecules, all bouncing around, hitting each other, lots of little forces, but the ball stays still. To make the ball move, you have to provide an external force, a force outside the ball. So children, out, become an external force. Stand here now. Now you pushed when you were inside, and I want you to do the same thing, but now you are not part of the hilux. You're an external force. Are you ready? Steady. Push. Harder. And there we are. They're an external force now. When they were in the hilux, they were an internal force. So you have to remember that Newton's first law talks about requiring a net external force. An external means outside the thing that you're looking at. Good. Let's go upstairs. Let's draw a free body diagram of the forces acting on the hilux. An external force is a force which is outside the system you're looking at. And when we say the system you're looking at, if I'm just looking at the hilux and everything in it is the system. If I was looking at a jet plane flying through the sky, the system is the aeroplane, the jet engines, and everything inside the aeroplane. An external force is outside the system. In the case of the hilux that we just saw, the system was the hilux and everything in it. So the first thing you need to do is decide what it is you're thinking about. If the problem is about a car on a hill, the system is the car. Ask yourself, is the net force inside the system or outside, i.e. external? And so now, net force. Well, if I draw a picture of a car on a level road, and I warn you, my whiteboard work is very poor. There's a level road. There is a car on a level road. There are the wheels. The centre of gravity of the car, let's say, is round about there. If I think of the forces acting on the car on a level road, then I have the weight of the car, W, pulling downwards, and that will equal the mass of the car multiplied by gravity, mg. And it's measured in newtons, force. I also have the reaction of the road pushing up on the car wheels there and there. But to make it simple, I'm going to show that as a simple force upwards, which I'm going to call R there. You notice I haven't drawn two little arrows there and there. I've just condensed it into one upward reaction force. And because the car is not moving up or down, R equals W. So that is the reaction of the road up on the car. There are no horizontal forces if the car is on the level. So the force diagram showing the forces acting on the car is simply the weight down and the reaction up. They are equal, so there is no net force. However, if my granddaughter comes along and pushes the car, then there is now a forwards push force, which I shall call F. But if the car is on a level road, there is no backwards force. And so there is an unbalanced force F, because there's nothing backwards to balance it out. And so the net force is F in a forwards direction, so the car moves forwards. And my daughter, being very strong, will make the car go faster and faster and faster. Now, let's think about if the car is on a slope. Let's draw a hill. And let's draw the car on the hill. Now, this is a worked example in your textbook, Fundamentals of Physics. If you've got this textbook, look on page 142, and this is page 143. Look on page 143 and you'll see this picture here with a worked example there. And again, it does what I just did. First of all, there is the weight of the car acting down. Now, if you think about that weight of the car acting down, it can resolve into two directions. It will have a resolution of force that way. So the car is now on a slope, and the road is a rough road. There's friction on the road, and the weight of the car is acting straight down, but because it's acting straight down, it can be resolved into two components, one parallel to the road and one at right angles to the road. Now, the road is pushing up on the tyres, so that stops the car disappearing into the road. So there's a reaction of the road on the tyres, which must equal the component of weight at right angles to the road, so the car doesn't disappear into a pit. But also there's a component of weight down here, and if you look very carefully at the worked example on page 143 in your textbook, you will see that the component of weight down there is W sine 15 degrees, because the slope of the road is at 15 degrees. So, if there is friction on the road, there's going to be a backwards force up there. Friction. So we have to take that into account in working out the net force. In that direction, at right angles to the road, the net force is 0. The car doesn't disappear down a hole. On the other hand, that way, there's a downwards force of W sine 15, and there's an upwards force due to the friction of the road. If that is bigger than that, the car will accelerate down. If that is equal to that, the car will remain stationary even though it's on a slope. So we have to work out how much friction there is, and we can work out what the downwards force is, and if the car is sitting there without running down the road, we can deduce that friction equals W sine 15. So look on page 143 of your textbook for the worked example showing the force diagram on a car on a hill. Now, remember Newton's first law. If you want to speed up, if you want to slow down, if you want to change direction, then you need a force. And the last thing I want to mention is a car going round a bend or round a roundabout. There's a car going in a straight line at a constant speed, no forces at all required if we assume there's no friction. If there is friction, then you have to have a forwards force to oppose the force of friction. On the other hand, if the car is going to go in a circle or round a bend, there was the direction of the car now, here's the direction of the car now, there's the direction of the car now. You have to have a force to cause the car to change direction. And if you are on a bicycle or even running round in a circle, you can feel you have to exert a force to pull you in to the circle all the time. So a force is needed to push you in to a circle. And if the car goes round the corner too fast, then the friction which is pushing the car in, the friction between the road and the tyres, is not big enough to push you in and you skid outwards. So when you're going round a roundabout in a car or on a bicycle, the reaction of the road on your tyres is pushing you in all the time. That's why on a bicycle you lean inwards so that you go round like that. Car, you don't have to lean inwards. But if you're going so fast that the friction force between the tyre and the road is not big enough, then it can't push you in enough. And so you skid and you fly outwards. Especially on a motorbike, you have to be very careful because you've only got two wheels. And if when you're going round a roundabout, the tyres of the motorbike hit a little bit of oil, suddenly friction disappears, there's no force pushing you in, and you fly outwards and fall off your motorbike. So, Newton's first law, you need a force to make you go round a corner. You need a force to accelerate. You need a force to decelerate. Newton's first law tells you what happens, but Newton's second law tells you how much force you need. So Newton's second law goes into a bit of mathematics, and that will be the next program to talk about Newton's second law and to do some calculations showing how it works.